afternoon, good evening, good morning, everyone. It's really a pleasure to be here with so plenty of people following our GGI Tea Breaks event. Today we have a focus meeting, and I want to thank Gian and Riccardo to accept to give this, to introduce this discussion on naturalness, and which has been the guiding line from the very beginning of my research. So I'm really curious. So Roberto, please introduce the speaker and welcome everyone to this event. Thank you.
Okay, so hello everybody. As Stefania said, this is a focus meeting. Is meant to be to have a first part in which there will be two talks presented by Riccardo Rattazzi from École Polytechnique and Francesco Giudice from CERN. And then this will be followed by a discussion which we hope will be as lively and interactive as possible. I anticipate that after the presentations, after each presentation, we will have a few questions which are really related on doubts or questions which might arise, technical ones which might arise on the presentations. And then I would postpone every comment or more general question until the end, until the discussion session. So if you have very urgent questions during the presentations, then you can use the chat, and then we will report the question to the speakers. The discussion session will be started by a sort of a mini panel of three experts: Martin Schmaltz from Boston University, Raman Sundrum from Maryland University College Park, and Liantao Wang from Chicago University, who will have been asked by us give the first comments or ask the first questions, just to as a way to initiate the discussion, which then will continue spontaneously. I will host together with Riccardo Torre, who should be around. I don't see him, but he should be here. Okay, very good. I will introduce the first speaker, who will be Riccardo Rattazzi, and then I will leave the stage to Riccardo as a chair to chair the talk by Gian Francesco Giudice. So let me introduce our first speaker. So Riccardo Rattazzi obtained his PhD from Scuola Normale, then made a list of several postdocs around the world at Berkeley, Rutgers, CERN, and then since 2006 he's been a professor at École Polytechnique at Lausanne in Switzerland. His research, I think, can be said that his research is focused on the many aspects of quantum field theory in a broad range, from particle physics to conformal field theories, condensed matter systems, and even cosmology. The contributions that had, I think, had the largest impact, I would rank among these contributions his work on effective field theories, anomaly mediations in supersymmetric theories, work on extra dimensions, his work on composite X theories, and then also, last but not least, the theories with the Galilean invariants, the so-called Galileons, and also his work that revived the interest on the conformal bootstrap. And I think it's I don't know whether it's an accident. I don't think it's an accident that most of, or at least many of this work have been done in collaboration with Gian Giudice. Okay, so I leave the stage to Riccardo, and again, so if there is any urgent question, you can use the chat. Otherwise, you will be able to ask technical questions at the end of the presentation. Please.
Thank you, Roberto. So the title of this focus meeting involves the future of particle physics. I will not talk about that, at least not today, if not forced. this is the title I was able to come up with based on what I will be saying. So what I have to say to introduce the discussion on the hierarchy problem is not original, but I believe it's also not what you hear most often. It's not the perspective you hear most often. The main point I want to make, again, it's not original, is that the hierarchy, the electroweak hierarchy, constitutes a paradox, and that this paradox is created in equal parts, but what we normally call the hierarchy problem, and by the attempts to solve it. That also is part is what constitutes the paradox, as I will illustrate. So, and to make the point, I will have to consider some basic notions of our discipline. So I don't think there's going to be any technical questions after my talk, because all the things I'm going to be saying are super elementary. So the first notion I want to, the first notion I want to consider, is the ability to use Keynote in Zoom. Okay, so the first notion I want to consider is the notion of effective theories. And let me illustrate. And there are the two basic aspects of effective theories, namely universality, also known as emergence, but I prefer the word universality, and reductionism. And this is very quickly illustrated by considering the electrostatic potential generated by localized charge distribution by observing it at a distance r much bigger than the size of the distribution. In this situation, we know we can expand the scalar potential in a multiple expansion, okay, the monopole, the dipole, the quadrupole, and so on. And this expansion amounts to an expansion in powers of the size of the distribution over R, okay? And now, what's the deal here? The deal here is that when you are at very large distances, okay, and you work at fixed accuracy, you only need a finite number of multiples to describe what you see. And really, to predict what you see, you can, for instance, measure the multiple that you need at your accuracy in a certain, by looking at the charge, at the potential in a certain solid angle, and that allows you to predict what happens in the other directions. Okay, so you can really predict. And this is universal. There's a notion of universality here because many different systems here, provided they have the same few multiples, will appear the same. Okay, so you're describing a manifold of systems. In other words, all your systems are characterized by a few parameters. On the other hand, if you, again, work in a fixed accuracy and you go to smaller and smaller distances, then you need more and more multiples. And of course, you learn more, you start differentiating different systems. You get more and more universality classes. And until you get to distances of the order of the size of the system where the expansion breaks down and you need an infinite number of parameters to describe what's going on. And of course, at that point, the description changes, and perhaps you will discover the distribution is only made of 3 point-like charges. And once you measure the position and the value of these charges, you can reconstruct all the multiples and predict everything. And this is the essence of reductionism. Okay, if you really want to understand what's going on, you really need to go to short distances and look behind the curtain of the size of the system. But it remains a fact that when there is a separation of scales, in other words, when you are at distances much bigger than A, then you don't need to know much about your system to be able to make predictions and do physics. Now, this example is static and classical, but the idea extends to quantum mechanics and to dynamical situations. And the textbook example of that is given, for instance, by the study of molecules in the Born-Oppenheimer approximation. Again, here you have a separation of scales, but these are temporal scales. The electrons are lighter, they move faster than nucleons, okay? The frequencies associated with them are bigger. And in presence of these separation of scales, you can solve the Schrödinger equation in 2 steps. First, you average over the motion of the fast electrons, and then you derive an effective description and an effective Hamiltonian for the motion of the slow nucleons. And this effective description can be refined order by order in the expansion of the ratio of the frequencies of these 2 motions. Very much like before, you were refining at larger distances your potential by adding more and more multiples and more power, so 1 over r. Again, you have the notion of universality because molecules made of different atoms, okay, provided they have the same number of atoms, can be described by similar Hamiltonians only by changing a few parameters. Okay. And again, this construction goes on everywhere in physics, and we are familiar with how to describe this in quantum mechanics. We call it integrating out. This 2-step procedure, again, when you have separation of scales, you separate the variable in the fast and the slow, and quantum mechanics just reduces all of physics to an integral. Of course, it's an integral that we don't fully understand, but it's an integral. And to do an integral, we can cut the space where we're integrating in the way we want and the way it is most convenient. And to describe physics and log distances, it's convenient to first integrate over the fast moving modes and derive an effective description for the slow moving one. And the example of molecules can be done precisely in this way. Okay. So now, all this to say, just to recall that, to restate that effective long distance descriptions are ubiquitous in physics. In fact, we may even say that the universality of this long distance description is the very reason we can do physics, okay? If we were dealing with a situation where at every scale we get something going on, something new, it's not clear to me how we would proceed. Certainly not in this, we would not have this universality. So the existence of separation of scales allows us to reduce many physical problems to just a few parameters and forget about the microscopic details. And now we think that this, in fact, the very fact that we can do physics suggests that, at least so far, and maybe for some time in the future, we expect that all theories of nature, sooner or later, they will manifest themselves as effective field theories. And in fact, QFT should be also viewed as just an effective theory like everything else. Of course, in the 50s and 60s, there was the idea that the quantum field theory was something fundamental, magic. But then Wilson came and explained that it was like everything else. Okay, so this is the very notion of effective description, effective theories. Now, there are some aspects of effective description that are crucial in order to make the point about the hierarchy paradox I will make later, okay? And these have to do with the notions of, 2 notions. One is simplicity and the other is naturalness. Now, what is simplicity? Simplicity, it's a notion that is also associated to the existence in effective description of accidental symmetries. And let me just say in a few words what I mean here. Very much like in the case of the multiple expansion I presented before, the long distance relevance of a finite number of parameters implies a great structural simplification. Okay, of course, you have a complicated charge distribution at log distance. You can describe it by a dipole plus a monopole plus a quadrupole. That's very simple. Okay, so there is a structural simplification when you look at things from long distances. And this simplification always entails, more technically, the occurrence of symmetries, the symmetries that we call accidental symmetries, okay? And these, again, they can be, the existence of symmetries in this perspective can be viewed as the consequence of the existence of a separation of scales. So when this suggests that when we see a symmetry, we say, oh, is this symmetry fundamental? Well, maybe we see the symmetry simply because we are looking at things from far away. Let me illustrate what I mean by this. Take an example. This is transparency. I've shown it tens of times, okay? Take a cow, okay? You look at it from nearby. It's a structured object. It has tail, horns, mouth. It's breaks rotation as much as it can. Okay, it looks different if you rotate it. On the other hand, if you look at it from far away, it looks like a point, and it looks like SO3 invariant. Okay, so we call this an accidental symmetry. It's an accident of the fact that you're looking at things from far away. Okay, but that's all there is. Okay, that's how symmetries arise, by looking at things from far away. In fact, the example of the multiple expansion allows us to make this simple cartoon example into something more mathematical. Okay, if you take and in fact, it has already all the features of the pattern of symmetry breaking, as I will just say in a moment. Okay, so you have this distribution, you compute your multiple expansion, and you have the monopole. The monopole is a contribution that respects the full SO3 symmetry. It's the one that, as you see from far away, everything looks like a point. But if you go to the next order, the symmetry is broken, okay, to a subgroup, but it's not fully broken. There's still a cylindrical symmetry, SO2, okay? So again, and then if you go to the next order, you go to the quadrupole there, you have all the parameters to completely break rotations, okay? So that's if you want, illustrates how symmetries arise, okay? Symmetries arise when you truncate to the leading multiple. And now, this multiple expansion is the same concept that appears when we do effective field theory, right? There, the notion of fundamental distance A is played by what we call 1 over lambda. And okay, this 1 over lambda here. And examples, again, textbook example of how accidental symmetries arise in effective quantum field theories is given, for instance, by parity in QED, okay? So in QED, the leading, in any quantum field theory, the analog of the monopole in the multiple expansion, the object that remains, the set of dynamical parameters that remain when you look at things at long distances or low energy or long times, is the part of the Lagrange which has dimension less or equal than 4, okay, which in QED up to field definition you can write in this form, okay, and there are these 4 terms. Now the 4th term in the case of U1, it just amounts to total derivative, so it's never important. So you're down to the first 3, and as we know very well, just without asking, just as a consequence of the field content and Lorentz invariant and gauge invariance, this part of the Lagrangian happens to be parity invariant. So the parity invariance of electromagnetism is, in this perspective, just the result of this, of the properties of the leading term in the multiple expansion of the effective Lagrangian. As a matter of fact, as soon as you go to the next order in the multiple expansion, you can immediately write a term that breaks parity. Okay, and in fact, this term is there induced by the weak interaction, just to show that nature doesn't give a damn about these global symmetries. Okay, this global symmetry, this parity just arises as an accidental symmetry simply because there exists a scale separation where we can truncate at a certain level of accuracy. Of course, if we are doing very accurate measurement, we are looking at very precise measurement in atoms, we will discover that parity is broken because of operators of this type. But again, the first accuracy, QED is parity invariant. So, and this symmetry is very much related to this beauty, in a sense, as it was seen in the early days, and simplicity of QED. And at least when I first started doing physics, it was percolating to me from the environment where I was, that quantum field theory was simple because it was fundamental. On the other hand, it seems it's the other way around. Things look simple because they're not fundamental. The cow looks like a point because you're looking at it from the top of a very tall mountain, okay? And when you get close, you get the fundamental aspects of the cow. You see, it's not that simple. So simplicity is, it seems that separation of scales and simplicity are in one-to-one correspondence. There's another, the other aspect of effective theories, or effect of any theories, that is related to symmetries, has to do with the notion of selection rules, which leads to the notion of naturalness, okay? So selection rules, okay? Let me talk about selection rules, okay? So what is the idea here? The idea, okay, maybe I don't know, I'm saying very basic things, okay? My whole talk is about basic things. And so you can always imagine, given any physical system with some parameters, you can always imagine symmetry transformations of the parameters of this system, okay? You can imagine that these parameters are like dynamical variables that transform under symmetries, and you can endow them with transformations such that formally your action is invariant. Having done that, having done this little trick, okay, then the dependence of physical observables on such parameters is just dictated by the covariance under such symmetries. In other words, when you write an equation that states how a certain observable is written in terms of fundamental parameters, this equation should be covariant. In other words, should transform under the symmetry in the same way, left and right. And the simplest obvious example of this idea is given by dimensional analysis. And as you can see, it as exemplified in the example of the pendulum, okay? And of course, it seems like Galilei, to whom all this baracca is being devoted, this thing where we are here giving our talk, it was the first to use argument based on dimensional analysis and also to look at the pendulum. Now, okay, the pendulum, there are three parameters: the mass, the length, and the acceleration of gravity. And then there are the dynamical, I mean, there is time and there is space to describe the dynamics, okay? So you can think of symmetries that dilate either time, space, or time, okay? You can view this as dilatations of time and space or changes of units with which you measure them, okay? Now, these are not real, the transformation, but they're not real symmetries, okay? But you can do as if they were real symmetries by allowing the parameters of our system to transform, okay, accordingly, okay, just the transformation that dictate, if you want, dimensional analysis, and then imposing the covariance under this symmetry. You have, for instance, the famous relation between the frequency of the pendulum and G and L, and in particular the fact that it doesn't depend on the mass, okay, up to some putatively order 1 coefficient, okay? So the reason why I'm showing this formula is because I just want to emphasize, because I don't know, of course it's clear to the vast majority of people, but I don't think it's clear enough that all we are dealing with when we talk about the hierarchy problem is an equation like this. Only in a context that is a little bit more complicated and more mathematical than the pendulum, quantum field theory, but it's precisely the same thing. And this is the point I really want to make. This is why I'm talking about these very simple things. Now, just going on examples of selection rules, the prototypical example of selection rule, if you talk to atomic physicists, has to do with atomic transitions or properties of atoms in electric fields, okay, similarly, okay, and here the prototypical example is, okay, the symmetry in question here is rotation, okay, and what you do, you take, for instance, an atom in its ground state and you slowly turn on an external electric field, which you can consider from the point of view of an atom as an external parameter, but actually in this case is truly a dynamical variable if you then go to electrodynamics. But for this stage, at this stage here, this is just some parameter, okay? It's some external parameter E, okay? And this parameter transforms formally in a certain way under rotations. And because of that, again, these selection rules dictate, for instance, that a quantity like the electric dipole that is induced by the turning on of this external field will be aligned with the field. In fact, will be related to the electric field in this way. And what dictates this equation is simply the fact that the left and the right-hand side have to transform in the same way. Again, this is another example of the same selection rules, notion of selection rules, that truly enters the hierarchy problem or the hierarchy paradox. In fact, getting closer to that, let me make another example, which may seem at first a little bit exotic. And it's the example here, the context is free field theory, okay, and free field theory that later will become interacting. And the symmetry I want to consider is the higher spin symmetry of free field theory, a symmetry that is not very famous, but which is there, and actually plays a role. I mean, if you look at the equation we work with on our daily basis in quantum theory, this symmetry plays a role, as I just want to illustrate. So take free field theory. We know that in free field theory, particles don't interact. So in any cell of phase space, in any momentum, for any given free momentum, the number of quanta in that cell remains constant in time. In other words, correspondingly, there is an infinite set of conserved charges, okay, given by these bilinears. The conservation of these charges is tightly related to the existence of a symmetry, which is made more manifest, which is made fully manifest if you work in momentum space. In momentum space, you can write this action this way, where phi hat is just the Fourier transform of phi, okay? This is a four-dimensional momentum, okay? And remember that phi is real, so phi hat of minus p is the dagger of phi of p. So changing the sign of p and taking the dagger is the same. In any case, this phi is a complex variable, and this guy here is this complex conjugate. So then it's obvious that this Lagrangian, written this way, this action, sorry, is invariant under phase rotations, okay? Provided this phase rotation, where the phase is just an almost arbitrary function of the momentum, provided this function satisfies this intertwining antisymmetry, which is what guarantees that after transformation, you still have the properties that its Fourier transform is a real field, okay? Now, if you look at this, that means that, for instance, if you expand this theta in powers of p, okay, as a polynomial, it starts with order p, then there is p cubed, p to the fifth. And the linear order p, you know it very well, right? This is just translation. And the corresponding conserved current is the energy momentum tensor, an object with two indices. Now, if you go to the second order, you get p cubed, and this, again, will give you some conserved current, and this will have two more indices, four indices. This is what we call a higher spin current, and you go on and on. And the presence of this current is precisely what characterizes that this theory is free, okay? As soon as the theory is interacting, this symmetry is gone, okay? As it can be, for instance, illustrated by the presence, by this case, consider phi to the fourth, okay? You introduce the interaction lambda phi to the fourth, and now the only way to abide, to have this symmetry be obeyed, is that this lambda is formally promoted to sort of a field, but it's more than a field, because a field depends on just one variable, okay? In momentum space, a field depends on p. This is like a quadrilinear, it's a quadrilocal field. It depends on four coordinates, okay? And if you write this interaction this way, of course, the realistic case, the physical case corresponds to this lambda hat condensed into a specific value where this is just some delta functions and forget. But formally, you can view it this way. And now, in order for the original symmetry to be preserved, then you have to formally dictate this transformation law of lambda. Okay, so lambda transforms with the phases that are precisely associated to all the four incoming momentum. Okay, and now it's so this symmetry now is what you can play with it. You can really see that this is what this symmetry tells you precisely what can happen when you combine internal lines into Feynman diagrams. Okay, and one way to see that is, for instance, to consider a very concrete question. Okay, which is again getting closer to the subject of this seminar, which is the hierarchy problem. Let me consider the electromagnetic correction to the pi plus mass, okay? So what we have here, we have an effective theory of a scalar, the pi plus, which is charged, okay, under electromagnetism, okay? It has, among other interactions, this vertex, which involves two pi's and the photon, okay? And the coupling is E. And again, I can promote this coupling E to an object that transforms suitably under these symmetries of the corresponding free theory, free electromagnetism and free pion, okay? You see here, there are three legs. So I put the phases of the pion, and the photon, okay? So whatever happens, okay, when I do computations, the selection rules dictated by this symmetry will have to be satisfied, okay, when I compute loops. Okay, I said this is an effective theory. We know that this is an effective theory where there's a more fundamental description dictated by a scale, lambda QCD. And there's another symmetry, formal symmetry, that I can consider in this case, which is dilatations. Namely, this is the symmetry under which we scale the objects with unit of energy by e to the sigma, okay? And all the other objects with the same way, of the same energy. This an object with dimension 2, I scale them e to the 2 sigma and so on and so on. This is just dilatation. Again, this is another formal symmetry. And now I can ask question about, based on these symmetries and the selection rules that follow from them, what should I expect for the two-point function correction coming from QCD, including electromagnetism, to the pion propagation. Okay, so it's a two-point function. There are incoming momenta PA and PB. And of course, when I will then condense to PA equal minus PB, this will become, I mean, this two-point function clearly will control correction to the pion mass. And now I can piece together powers of E and powers of lambda to precisely match the quantum numbers of this two-point function. And this is just a game that we do all the time. This is a two-point function. We'll have to have dimension 2. So I have to put 2 powers of lambda QCD. And then if I put a power of E, I have to put another power to compensate the symmetries, because this result here has only 2 pion legs and should transform with corresponding phases of PA and PB, which are given precisely by this. Okay? And then you can combine it this way. Okay? This suggests that according to selection rule, very much like for the atom in the electric field, very much like the pendulum of Galilei, I expect that the pion will receive a correction to its mass that scales like this. And in fact, this is precisely modulo a 16 pi squared. If you are slightly more clever when you do the computation, what you get when you do what we discussed in BSM or people like that do, when we want to estimate the pion mass, we take the loops, we say, oh, this is quadratic divergence, quadratic divergence, cut it off, cut it off, cut it off, and we get this. All that we are doing here is simply enforcing the selection rules of our background symmetries, okay? I think it's correct to do that, cutting it off, but for those who believe that this is just something that doesn't make any sense, I'm just saying that this makes as much sense as what we learn in physics 1 when we do the dimensional analysis of the pendulum. And now with the notion of how much time do I have?
I think you have at least 13 minutes.
Okay. Okay. So the notion of selection rules brings us directly to the notion of naturalness then, okay? Now, in quantum mechanics, observables are obtained by doing a path integral. You have quantum fluctuation, you have all possible trajectories, or if you want, you have all sum of amplitudes or Feynman diagrams. So an observable can be, is normally written as the sum of various contributions that you can associate them to amplitudes, okay? And we can always think of symmetries under which is observable transform and under which the parameters transform in such a way that each and every term in this sum will respect the selection rules associated to this equation, okay? In other words, the dependence on the couplings, on the parameters of the theory will be precisely the one dictated by symmetry, up to coefficients, which we can call them order 1 coefficient. And in such a situation, then we can clearly distinguish two cases, one ordinary and one extraordinary, okay? The ordinary one is the one we call natural, is the one where all these contributions are never cleverly conspire against each other to give you something smaller. In other words, when it's a situation where when you measure experimentally is observable, the result is roughly of the order of the maximum of this contribution, if there is a maximum, okay? On the other hand, the situation that is less ordinary is the one where some of these contributions cleverly conspire against one another in such a way that what you measure is way, way smaller than them, okay? This is what we call unnatural, okay? I mean, both situations are possible. As I said, this is undoubtedly more ordinary and this is less ordinary. Now, what to say of this case? Well, the first thing to think if you are faced with this is that perhaps you haven't considered all the symmetries, okay? In some cases, there may be some contributions that are related and you haven't been clever enough to identify the symmetry. Or it can happen, okay? It can happen even if that is not the case. And it seems, I mean, from our experience, I would say that this happens when it can happen, and meaning that when the system has the option to try to make this happen. And this is, at least in our ordinary experience of physics, this seems to happen when and only when you have a manifold of possibilities, okay, and of similar systems that you can pick from. And among this big variety, there will be one where this seemingly rare abnormal accident happens, okay? And systems in condensed matter are the prototype of this, okay? There, the system exists in a variety of control parameters. One of these is, for instance, the pressure, okay? And the physical quantity of the system will depend on these parameters, and there is the possibility of choosing in this landscape of possibilities of the parameter situation where something abnormal happens. Okay, this is just an example of this. Take, for instance, it's given by this antiferromagnet, okay, you can find in the book of Sachdev, okay. This is an antiferromagnet, so the relevant variable is a sort of magnetization, but is an anti-magnetization. Is the spin density sum, is the spin sum with a specific -1 that in such a way that even if the spin is opposite on nearby sites, for this variable, they sum up, okay? So this field is something that looks very much like the Higgs field, and it transforms like a triplet under rotations, and it will have a Lagrangian, okay, in particular a potential, and the potential again looks like the Higgs field. If it wasn't for the fact that solids, you can put them in a vice, okay? For those who don't know English, like me, the vice in Italian is la morsa, okay? The thing that you crank out when you, if you've seen Goodfellas, I mean, this is Goodfellas, then you can remember what this is, okay? And you can change the pressure, and as you change the pressure, for instance, the quadratic term, which is you can call the mass, which normally has a size which is dictated by atomic physics, because there are various contributions, but there's a specific value of the pressure where this vanishes, okay? And this is where it looks like the ordinary selection rules of atomic physics are not good for you to guess what the result is, okay? This is a special case. Of course, in other words, you can undo the natural expectation from atomic physics by tuning the pressure at a critical value in a landscape of possibilities, okay? Now, this is one way to get things that look unnatural or not ordinary. And I guess what Gian will have to say during his talk is a way, he has a vice, which he's using or if he has a quantum vice that oscillates somehow, so that somehow it will be at the critical thing. I'm curious to see what he will have to say, but that's a possibility, okay? This is not to tell you that this is impossible, this happens. Of course, it could be that we live in a world where there's some external condensed matter physicist cranking the vice. That would be terrible, okay? Okay, so, and the naturalness criterion of TOF is just a consequence of what I just said. Okay, you can ask the question, under what condition is a quantum field theory natural or unnatural? Well, you can view quantum field theory as an effective theory. Here, there's the UV description, the IR description. And again, you can integrate out the UV and find the effective coupling of the IR description. They will be precisely like the observables I was describing before. These effective couplings are like observables computed in terms of the more fundamental couplings. And again, very much as I said before, the relation between the GI, the little GI and the capital GI may or may not be natural, may or may not deviate dramatically from what you expect from selection rules. If it doesn't, then you can easily convince yourself that the pattern of GI is consistent precisely what dictates with the predicates of TOF naturalness. So in other words, all this is just another way. I mean, TOF naturalness just follows from applying this notion of naturalness to effective field theory. Okay, so now that I've given you the basic concepts, let me now try and apply them to the standard model and to its possible extension. Okay, so the basic notions are the notion of simplicity that arises, it seems to arise whenever you can separate the scales and you look at things from far away, like the cow. Okay, and the other notion is the notion of naturalness, which may or may not exist. Okay, depending on whether you have a landscape to choose or not. Okay, so let me consider the standard model, and let me consider the standard model in this effective field theory perspective. Now, in my mind, I mean, our modern perspective is that the standard model is not described by this normalizable Lagrangian that often we call the standard model. The standard model is defined by the gauge symmetry and the field content. And once that is done, you write everything. Because otherwise, it's like saying, if I were to truncate the normalizable part, it's like saying that the charge distribution is just given by a monopole or by a monopole plus a dipole. No, there is everything, okay? So the standard model consists of, what the hell is not going on? I'm stuck. Okay. Okay, so the standard model it should be viewed as a multiple expansion, very much like the first example I started with, okay? And here you have the analog of the, if you want, the monopole is given by the normalizable part, and then the higher multiple, the one that contains the structure, and that in principle can break the symmetries, very much like for the charge distribution are coming from dimension 5, 6, and more, okay? And now it's interesting to really see, given the quantum numbers, given all, I mean, in principle, we could write everything here, we break, there's no accident, everything, it's a mess, okay? But if we are in a situation where, for some reason, lambda is very large and it makes sense to do this expansion, it makes sense to look at this term by term. And let me start first with the one that would dominate, okay? In fact, also LD equal 2 would dominate, but that's, let me just, for a rhetorical artifice, start with the D equal 4 part. Now, this is, what is remarkable about this LD equal 4 is that what can I say? With the exception, if you want, with the exception of the QCD theta angle, which is an exception, which I don't think changes the overall picture I'm going to make. Here, I mean, this LD equal 4, the four-dimensional part of the standard model Lagrangian accounts beautifully and very simply for all that we see and for all that we don't see. Okay, so there are the gauge coupling, the Yukawa couplings, the Higgs quartic. These are all things that we have observed and that we have measured and explained things we see in particle experiments. But this Lagrangian also has accidental symmetries and accidental properties that are crucial to explain the pattern, what we see, or if you want, also what we don't see. In particular, this Lagrangian, very much like the cow in the very far away limit, has some accidental symmetries that were not part of what you were supposed to ask, and these are the lepton numbers and baryon number, okay? And one consequence of these symmetries, okay, if they were sufficiently good, is that we can have this talk, and then other things is that neutrinos are massless because of this symmetry, okay? You may say, oh, this is bad because neutrinos have a mass, but come on, neutrinos have a tiny mass, okay, a mass that is way, way smaller than the mass of the electron. Between the electron and the up quark, there's a factor of 10, and between the electron and neutrino is a factor of 10 to the 7, okay? So there's clearly something different between the neutrinos and the others, and the very fact that at the first order, if you're at the monopole level, the neutrinos are massless, and you have these symmetries that are very much what we see in nature. Lepton numbers are conserved, baryon number conserved. Other thing, flavor and CP. In this Lagrangian, flavor and CP violation come fully from, again, with the exception of theta, fully from the Yukawas, okay? And because of that, this induces this amazing G mechanism, which if you think of it, is really amazing. Because of the G mechanism, for instance, the electric dipole moment of the electron comes at 3 loops. And 3 loops, and it is suppressed by mixing angles. which per se, they're not even so small, but they pile up and they give you a tiny result beyond presumably what we could do even in the next generation of experiments. And other things, the custodial symmetry, there is a lot, okay? It's truly amazing how it's remarkable. It's truly magic, this Lagrangian. And it's even more magic when you consider the next orders, if you go to the higher multiples, because all these properties are gone as soon as you cross this dimension threshold. In other words, as soon as you go to effects that vanish in the limit when you send the structural scale, length scale to 0, you start seeing that lepton number is violated, neutrinos can get a mass, flavor is violated, you have all crazy phenomena, U to E gamma, things that we haven't seen at the level of 10 to the minus 14 branching ratio. You see anomalous effects in delta MK, which is pretty tiny, but you would get bigger effects. You get all sorts of EDMs easily, and more amazingly, proton decays, okay? And the very fact that, as I said, the counterpart that the absence of all these effects explains what we see very well, goes along with the fact that the non-observation or the observation of this effect at a small level, like for neutrino masses, dictates very, very high scales, okay? So the scale that for instance, we need to explain the neutrino masses can easily be 10 to the 14 GeV. Of course, you could have a smaller scale with smaller couplings, but you could easily imagine a situation where the next layer is 10 to the 14 or higher GeV, perhaps of the order of the Planck scale around there. Proton decay would be fine, flavor would be far fine. We can discuss about the strong CP problem, how it fits in there. Perhaps the real scale is lower. Anyway, it seems like these issues fit very well in a situation where the next layer is very, very, very high. In other words, there is simplicity at play in the standard model and in what we see in nature. So let me say that if you take the standard model with a very, very high fundamental scale, you nicely account for both what you see and what you don't see, okay? But as we know very well, there is a term which, for specific rhetorical reason, I avoided to discuss, and that is the D equal 2 part, which is the Higgs mass, which is precisely what is responsible for the scale where we're doing experiment like the weak scale, okay? And all this makes sense, provided there is a scale separation, but the Higgs mass grows, at least at face value, with this fundamental scale. It grows with a coefficient we have to debate, and we will debate it in a moment. But it seems like unless this coefficient is very, very tiny, this seems unnatural, okay? And to make this more quantitative, we can go back to the selection rules we discussed before, and which is another way, but just to say what we normally say when we give a class in DSM, we say, oh, there is this loop, the quadratic divergence, and then people just say, oh, but quadratic divergence, I used in reg, go to hell. No, okay? This way of estimating the correction to the Higgs mass from the microphysics is just a way to enforce the selection rules associated with dimensional analysis and the higher spin symmetry, okay? So in other words, this computation here is simply telling us that generically in a theory where there is this coupling, which there exists in the standard model, and there exists a physical scale, there's going to be a correction that scale like this to the Higgs mass. Similarly for the gauge coupling, similarly for the Tourneton. And this is precisely what happens in any decent construction that explains the origin of the Higgs mass, like in supersymmetry or compositeness, okay? Nothing surprising. This construction precisely realize the selection rules that I described before, okay? But then, of course, if you bar any cancellations, as we know very well, then the fundamental scale has to be very low, much lower than what is suggested by the observed simplicity. So it looks like we are at a loss because we cannot have both simplicity and naturalness. If we go for simplicity and the fundamental scale is very, very high, we really understand quite a lot, very simply by dimensional analysis about the world we live in, about its structure, about this approximate symmetry, about the very fact that we are giving this talk. But this is very unnatural. Okay? On the other hand, if we bring the fundamental scale very close to the weak scale, and we have a chance to be natural as concerned, for instance, the Higgs mass, then it looks like we cannot argue for simplicity as easily as we did before. Before, simplicity was simply coming from dimensional analysis, okay? Because all the effects that were inducing complexity were coming from higher dimensional operators, okay? How much time do I have, Roberto?
0. I think we are a little bit over time, so.
Oh. Okay, well, I can finish here. I just want to say that this may be, the conclusion here may be fast and loose, because there may be some clever guy who can construct a theory here, which is both natural and where above this scale, it has precisely the same magical property of L4 in the standard model. And this, if you want, is the task of the would-be task of BSM, okay? And this is where we get precisely to the other side of the problem, okay? As I said, the paradox is both having to do with the standard model and about the attempts to go beyond. So the ideal, okay, and I'll be finishing in a minute, the ideal here would be to have a upgrade of the standard model around the weak scale, where you have a new standard model, call it BSM, okay? And in this new theory, the scale separation between whatever new scale exists above, maybe the Planck scale, maybe whatever else, is natural. And the new theory shares precisely the same magical property of the 4-dimensional Lagrangian standard model. In other words, at the level of operators dimension less or equal than 4, it has all the accidental symmetries that help explain what we see and what we don't see. The question is whether this can be realized. And the answer is, we know we have only to be able to come up with only 2 options in 40 years, and none of them really works in this sense, okay? In the case of supersymmetry, there is a zillion of new contributions that break flavors, CP, baryon, and lepton below dimension 4. The very fact that you have scalar quarks and leptons induces a lot of new effects. Of course, you can go around it. We've devoted careers to making this to work, but it's not as automatic and simple and as explained in 1 minute as it is in the standard model. It took 40 years to do models. It's true that some of these could be the right thing. Like, for instance, gauge mediation goes as close as it gets to the standard model, but not completely. And in the case of composite Higgs, the situation is reversed, okay? It's not that you get unwanted things at dimension below 4. It happens that the things that you want have dimension bigger than 4, because the Higgs is now composite operator. The dimension of the Yukawa couplings is bigger than 4. So the Yukawas, which you observe, goes in the same basket as the thing that we don't want to see. And that is making things complicated. So automatic simplicity is lost. And it seems there's no free lunch. So if you have the new physics much above the Higgs mass, this beautifully accounts for the observed structural simplicity of particle physics, but is not natural. And conversely, all natural extension of the standard model, and we took this really, this is what I'm saying is the other side of the problem. It took many years and work, and we got convinced of this. I mean, it's working proof. I mean, working in BSM is just proof that all natural extension of standard model need to be retrofitted with some ad hoc mechanism in order to reproduce the simplicity of observation. So there's no free lunch. This is the hierarchy paradox. Thank you, and sorry for going over time. I have more things to say, but if you want, I can say them during the discussion.
Thank you very much, Riccardo. So I will see if there is any technical question on your presentation. People can raise hands or write in the chat. Again, I would leave comments or more general questions to the discussion session.
Thanks, Roberto. So I go ahead.
Yes.
So I have the pleasure to introduce Gian Francesco Giudice. So Gian will give the next talk. Is obtained his PhD from CISA and Trieste. He held research positions at Fermilab, University of Texas, and the EPFL. And in '93, he moved to CERN, where he's currently the head of the theory department. His research focuses on generally on formulated new theories of fundamental interactions and studied the implications for early universe. For instance, he gave influential contributions in supersymmetry, extra dimensions, electroweak physics, flavor, collider physics, dark matter, leptogenesis. Among these contributions, probably the most influential were the Giudice-Barbieri criterion to test naturalness, anomaly mediation, split supersymmetry, the Giudice-Mazero mechanism, minimal flavor violation, and the Higgs boson potential, and quantum criticality. I want to also remember that he's the author of a successful popular science book titled Zeptospace Odyssey, which is devoted to particle physics and the LHC. I think that what Gian will discuss is the hypothesis on which naturalness principle rests, the consequences of relaxing some of these hypotheses, and the current attempts to develop new paradigms beyond naturalness. So thank you, Gian, please.
Thank you very much. Can you hear me?
Yes.
Very good. So thank you very much, Riccardo, and also the other Riccardo for this beautiful presentation on naturalness. I think you cover the subject so well that I don't have to add much other than some personal thoughts. By the way, if there is still anyone in physics who hasn't understood what naturalness is, I strongly recommend Riccardo's lectures at the GGI last January, because I think they're really illuminating on the subject. So here we go.
I'm surprised you have looked at them.
I did, but I can't turn. I can't turn.
If you click,
I did click. Can I,
Arrows.
well, it happened and it didn't happen.
Exit the full screen and
Try again.
go back and down.
No.
No? It worked before.
What? It doesn't. It just says.
So, and what if you use the arrows on the keyboard?
That's what I'm doing.
Click, otherwise click on the desk.
Right.
Yeah.
Ah, here we go.
Okay.
Yeah.
Thank you very much. Sorry. So naturalness is a powerful tool provided by quantum field theory to explore the properties of the theory beyond the boundaries of what has been tested experimentally. And it enters the game when some parameters of your effective theory are very sensitive to the heavy modes that you integrate out. And this gives you information about the maximum energy up to which you can extrapolate your low energy description. In a sense, it's an alarm bell that your description is incomplete. So when the alarm bell goes off, the obvious next step is to look for the missing pieces, for the new physics that accounts for naturalness. But what happens when you don't find these missing pieces? And this is not such a hypothetical question, because this is the indication that we have received on one side from the LHC so far, and on the other side from the cosmological constant. Well, in this case, one has to question the hypothesis on which naturalness rests and see what are the consequences of dropping some of these hypotheses. So let me analyze the hypothesis on which naturalness is based and see what happens when these hypotheses do not hold. First hypothesis is scale separation. The framing of the problem of naturalness is based on the existence of multiple energy scales, well separated. So if you take the standard model in isolation as a renormalizable theory, you can't even formulate the problem because there's no hierarchy of scale to start with. There are no heavy particles that can affect quantum mechanically.
There's the Landau pole, Gian.
So yes, new physics, exactly. That's what you're putting. So the question is, are there any new energy scales above the weak scale? I think we have good reasons to believe that the most plausible answer is yes. Quantum gravity has a scale associated with the Newton's constants, which is a Planck mass. Actually, from the dimensional analysis point of view, the Planck mass is not a mass, but it's very plausible that it corresponds to some new heavy modes. Other indications come from neutrino masses, a strong CP problem, inflation, gauge coupling unification, and so on. So none of these are indisputable evidence, but I think they provide very strong indications for the existence of new heavy modes in nature. And more in general, if you want to understand and compute any of the 28 free parameters that enter the standard model, it seems unavoidable to introduce new physics. While we have strong reasons to believe that, that new short distance scales must exist, we have to keep in mind that this is not guaranteed. For instance, this hypothesis was challenged by large extra dimensions, which try to bypass naturalness by postulating that there's no scale separation in the real world, or it is pursued by approach inspired by asymptotic safety in quantum gravity. It's a very ambitious assumption, but it is also very hard to reconcile the idea of no scale separation with the real world, unless you're willing to renounce to find any explanation for the structure and the parameters of the standard model. I don't think that this is a very fruitful way of thinking. So in conclusion, I believe it's very difficult to challenge hypothesis 1. So let me come to hypothesis 2, the validity of effective field theory methods, which is what Riccardo was alluding to before. So the naturalness principle relies heavily on the effective field theory approach to quantum field theory. Basically boils down to the quantum mechanical effect of parameters being sensitive to modes integrated out from the low energy theory. So when the sensitivity is very strong, it violates the Wilsonian intuition of EFT. So the question is, could it be that the rules of EFT break down? Of course, this would be a revolutionary result. For centuries, physics has made progress exactly because natural phenomena can be described layer by layer. Newton didn't need to know about the atomic structure of matter to compute the orbit of the moon around the Earth. Bohr could compute the atomic levels without knowing about the existence of quarks and gluons. With the EFT hypothesis, we can give a consistent physical description within a certain energy range without full knowledge of physics at arbitrary short distance. It's not guaranteed that nature satisfies the EFT hypothesis, but this hypothesis has been the very reason for why physics was able to make progress, which is a point that also Riccardo made. Progress in physics can proceed step by step without requiring simultaneous knowledge of physics at all scales. So you see that dropping this hypothesis would be a complete revolution of our approach to understand particle physics and the physical world. It's actually so revolutionary that we don't even know how to formulate a concrete example of how this could happen. This would require some magic interplay between infrared and ultraviolet, introducing some correlations such that total quantum corrections to an IR parameter is much smaller than the single contribution coming from the UV. And remember that parametrically, the UV contribution is expected to be by far the largest effect. So this magic correlation between IR and UV is something that completely defies the EFT logic. If something like that happens, then this magical phenomena would require the breakdown of the concept of locality in QFT, enough to shatter quantum field theory, which is the very language that we're using to describe the real world. Nimar Kanihamed, in a recent talk, has been playing with this idea, which I find fascinating. But we're still very far from getting out of these ideas anything close to reality. However, there is one indication that EFT may not catch the full physics story, even in the low energy domain, and this is a swampland. The various swampland conjectures state that not all theories that are allowed by the usual rules of EFT, by symmetry, selection rules, necessarily have a consistent UV completion in the context of quantum gravity. There could be restrictions of the IR theory that are completely inexplicable from a low energy point of view. Of course, this is not sufficient to say that IR-UV connections are possible, but it exposes the limitations of thinking only in terms of low energy theory. In conclusion, I say that exploring the possibility of dropping hypothesis 2, which is this EFT hypothesis, actually what Riccardo was calling scale separation, is a very interesting adventure. However, it is a very difficult road to pursue because it really requires to blow apart some of the founding principles of quantum field theory. So high risk, high gain. This is an interesting direction for crazy people with great ambitions. Let me come to hypothesis 3. IR free parameters are calculable in the UV completion. This is, of course, the central hypothesis of the naturalness principle. Whenever we formulate the question about the naturalness of the Higgs, we tacitly assume that the Higgs mass is a calculable quantity within a more fundamental theory. For instance, in supersymmetry, the Higgs mass is given by a combination of mass parameters that break supersymmetry and those that break chiral symmetry, mu. This is not surprising since the Higgs mass is protected by these symmetries combined together. So either there is a special and unexpected relation between UV and IR, and this is the breakdown of the hypothesis 2 that I was discussing before, or the mass parameters that control the relevant symmetries are not much larger than the Higgs mass itself. And this is the usual statement of naturalness. And the story is the same for the composite Higgs. The Higgs mass is a loop factor below the mass scale of new resonances. And here I've taken the top Yukawa coupling as a source of the breaking of the shift symmetry that protects the mass of the Higgs when is an exact Goldstone boson. Again, either there is some magic IR UV connection that must be explained, however, or naturalness implies that strong dynamics is not far from the weak scale. So now the question is, can we give up hypothesis 3? Well, one trivial way to say is, well, the Higgs mass is not a calculable quantity. It is a God-given number, and knowing its origin goes beyond human comprehension. Okay, this is a possible attitude. It's not a very scientific one, because what we have learned from studying nature is that nature is comprehensible, to paraphrase Einstein. And it is the duty of fundamental physics to uncover the laws of nature. So just stating that the Higgs mass is what it is not a very meaningful statement for me. However, there is a more interesting way in which hypothesis 3 could break down. And this is the case in which the IR parameter does not correspond to a unique expression in terms of UV quantities, but is a function of some field whose value varies during the cosmological history or throughout a complex vacuum structure realized in the universe. And this point of view is a profound paradigm change with respect to the usual approach based on symmetries. Some people have little sympathy for this approach because they see it as a way of renouncing to attack fundamental physics problems, a way of deferring the question of computing physical parameters to the cosmological history or the structure of the multiverse or to environmental considerations. But I really believe that this is not true. This is a radical change in perspective, but it's deeply rooted in physical theories and can lead to precise predictions. So for me, this direction is very intriguing and offers a wide range of possibilities still largely unexplored. Now we'll come back to this in more detail. So at the moment, let me maybe summarize what I said. So naturalness is a powerful tool for extrapolating our knowledge beyond the boundaries of what is explored by experiment and infer the scale where a certain EFT must break down. And retroactively, when applied to known phenomena, naturalness can be used to make postdictions, or more interesting, to elucidate the origin of certain parameters and their relations with symmetries and EFT rules. And there are several examples. The existence of the positron, the rho. This examples was given also by Riccardo, who explained in the chart. I've discussed these examples in other occasions, so let me skip here in the interest of time detailed discussion. The point that I made today, however, is that just like every other principle in physics, the naturalness principle relies on certain hypotheses. What I've shown is that giving up naturalness by relaxing one of these hypotheses is certainly possible, but it often leads to consequences that are even more radical than those of naturalness itself. It may lead to a true change of paradigm. This is the revolutionary legacy of the LHC results. The conventional road to naturalness led to amazing concepts in physics: technicolor, supersymmetry, composite Higgs. They imply new particles, new types of forces, new symmetry structures, a new vision of space-time. These are grand ideas, but they are based on an approach that I could define conservative, in the sense that it is an extension of the successful approach that led to the standard model. So let me call this approach the symmetry paradigm, because gauge symmetry of a Lagrangian play the role of the underlying principle behind this approach. And this paradigm has dominated particle physics for the last 50 years and has been extraordinarily successful. But the non-discovery of new physics at the LHC may be a clue that the paradigm is running out of gas. It may be a clue that gauge symmetries are not as fundamental as we thought, but are only an emergent phenomenon. They could be a mirage of a different reality that takes place at a more fundamental level. Maybe what the LHC is telling us is that it's not just a matter of adapting our models or changing the gauge group, adjusting some parameters. It's really time to look for radically different paradigms. And of course, the results from the LHC are not the only clue. Obviously, there is another experimental clue that speaks in favor of a paradigm change, and this is the cosmological constant. From the EFT point of view, the problem with the cosmological constant is identical to the Higgs mass. The only difference is that the cosmological constant is not an observable in quantum field theory, but becomes an observable only when you turn on gravity. But this is classical gravity, so I don't see a substantial logical difference unless something magical happens at the level of quantum gravity. And decades of attempts to explain the smallness of the cosmological constant using the symmetry paradigm have not led to any decisive progress. On the other hand, like it or not, Weinberg's anthropic approach gives a logical, consistent, and conceptually simple framework. And it's based on the assumption of the multiverse. For me, this is the really fundamental aspect, not just the use of the anthropic argument as for selection, but bringing in the multiverse as the arena in which we address physical questions. I don't think that the multiverse is withdrawing from finding physical explanations. So, on the contrary, it's a way of redesigning physical reality, the structure of the vacuum, and the history of the universe. It affects our basic understanding of the principles governing the universe. It's a new Copernican revolution, in the sense that not even the patch of the universe we live in is special. A total revision of the cosmological principle, because the universe is approximately homogeneous and isotropic only within our horizon, but maybe globally highly non-homogeneous. Compare ourselves with an imaginary astronomer who lives on a planet in a solar system surrounded by a dust cloud impenetrable to electromagnetic radiation. So all that the astronomer can observe are the planets and the sun. And he gets obsessed with the idea of computing from fundamental principles the planetary distances and orbits, because this is all he can see in the universe. And logically, he ascribes a fundamental meaning to those numbers because that's all there is to measure. Then one day, a theoretical physicist comes and tells the astronomer that maybe the universe is very different from the way it looks. She claims that there are complex structures beyond the dust cloud, and that the measurements of planetary distance have to be interpreted in the global context of a larger universe. And hers is not pure philosophy. It's a precise statement about physical reality. The problem is that it's difficult to measure what's beyond the cloud, but that doesn't make the hypothesis on physical reality less scientific. It only makes the life of the astronomer harder and forces him to think harder on how to advance knowledge. We are in a similar situation, and since physics is a natural science, we must think harder on how we can test our hypothesis. Anything lamenting about the difficulty of the task is not a justification to discard hypothesis. I think it's like what happened with inflation. When it was first proposed, it sounded like a fascinating idea, but some people found it too abstract, because beyond the domain of empirical physics, because it was considered impossible to test. Then people realized about its potential for computing structure formation. And today, observational cosmology is a field of precision physics. So my point is the following. The results from the LHC had an explosive effect on theoretical particle physics. As a result, today we are confronted with a conceptual crossroads. One possibility is that our original perspective was correct, but maybe nature is more malicious than what we expected. And this is the point of view that was advocated by Riccardo. He presented in a very sharp and convincing way. Nature was confronted with this choice between simplicity and naturalness and couldn't really make up her mind. And so she opted for a compromise between the two. And this is a possibility. And this makes the life of experimentalists a little harder, but not all hopes are lost. We simply need to look a little deeper. It could well be that the point of view of Riccardo is correct. But what's more important is that, whether Riccardo is right or wrong, that we have the experimental tools to get to the bottom of these crucial questions. So further experimental scrutiny is as motivated as ever. Whatever the answer is, we will expand our knowledge in a fundamental way, and we will be able to use that knowledge to direct future theoretical search. And moreover, I should say that recent experimental results have, for me, reshuffled the cards. The B anomalies from LHCb, and in particular the new results on RK, if true, indicate a structural change of the standard model. We are seeing something, if true, that cannot be explained simply with a minor modification of the standard model. If this is true, really, these results make the flavor structure and the symmetries of the standard model crumble under the weight of this new unknown dynamics. Our inability of explaining the flavor structure is the most evident and embarrassing, I would say, problem that particle physics is confronted with. We often lament that we don't know what dark matter and dark energy are, together with 95% of the universe, or that we don't know how to compute the Higgs mass. Well, the truth is that we can't even make sense of the other 5% of the universe, because can we compute the electron mass? And the electron mass was discovered more than 100 years ago. So it could be that the measurement of RK will become a key to unlock this puzzle. And the measurement of G-2 does not necessarily revolutionize the flavor structure, but it adds gasoline to the fire of this consideration. So these measurements could be a game changer and reestablish the symmetry paradigm as a winning strategy. We are doing research at the very frontier of knowledge, so we should be used to these sudden changes of directions, because they are a part of the game. And so Riccardo may be right that this is a direction to go, and that RK and G-2 are certainly having a big impact also on the way that I imagine the future of particle physics. But suppose for a moment that the B anomalies and G-2 do not withstand future scrutiny. And so nothing new comes out from the LHC. Well, then, as a theorist, my natural inclination is to give a different interpretation of the absence of new physics at the LHC. This compromise between naturalness and simplicity could be an answer, but my natural inclination is to read a different and more radical message in the LHC data. The message is that we need to break with the past and look for new paradigms. And as I have discussed, some of these new paradigms are a complete change in direction in particle physics. They require either a modification of quantum field theory, or, to be more modest but more realistic, a modification of the vacuum structure of the universe or its history. Either way, this requires a profound redefinition of some of the outstanding questions in fundamental physics. So, for instance, in particular, it calls into question the meaning of the program in the quest for final unification. But let's see concretely what are the options for moving away from the symmetry paradigm. One trend that has emerged in the last few years is a very bottom-up approach. So instead of starting from big principles, one constructs prototype models that describe new physics that is light, but may have escaped detection simply because nobody has looked for them. And the most common examples are called the fabulous five. So these are milli-charged particles, axion-like particles, heavy neutral leptons, dark photons, and dark Higgs bosons. This approach for me has a value for particle physics. One, it helps theorists to think out of the box. And this is of great value when the community is looking for new directions. Two, it helps theorists to think about new experimental techniques. And recently, we've seen many examples of new proposals for radically new types of experiments where theorists had a leading role. Think of Abracadabra, Phaser, Sensei, Ariadne, Casper, Methuselah, and so on. Okay, another point is that it helps to create a strong theory and experiment collaboration. As I said, we've seen many very positive examples of this exchange. It also helps building links with other fields. Astrophysics, atomic physics, nuclear physics, condensed matter, and so on. This is because these new experiments borrow techniques from other fields. It creates a more diversified spectrum of experimental activities. And I think this is an important point because in an age in which the time scale for collider experiments is getting longer and targets are mostly exploratory, particle physics needs a great variety of experimental projects with different approaches. And the last point is that serendipity means opportunity. While I think that it's clear that having clear targets is important, the field is in an exploratory phase, and we cannot tell which is the winning direction. So searches guided by experimental opportunities may turn out to be the winning strategy. So for all these reasons, I'm a great supporter of this approach, which has great value for physics. However, just among ourselves, the few of us, I should add on a personal note that this approach does not resonate with my views on theoretical physics. It's only a matter of taste, but for me, theoretical physics should go after fundamental questions. Its goal is to identify principles. Models are useful, but they should be, they must be the consequence of principles, not the starting point. Let me quote Steve Weinberg on this subject. Despite its value, positivism has done as much harm as good. Today, positivism has preserved its heroic aura so that it survives to do damage in the future. For me, pure thought is a warp drive that propels physics into revolution. So let me take from the rest of the talk this more idealistic point of view and ask the question, is there a context in which we can formulate a paradigm which is alternative to the traditional symmetry paradigm? I want to argue that the multiverse is a useful setup for addressing this question. Let me, however, first explain what I mean by multiverse. I will use a rather broad definition. probably broader than it's used by most people. I will refer to the multiverse when low energy parameters are functions of fields with a non-trivial vacuum structure, which is explored during the history of the universe. Notice that I don't necessarily require that today every patch of the multiverse is populated. We know that eternal inflation is a natural and efficient way of populating different vacua of a theory with a complex vacuum structure. But I also include in the definition the possibility of a transient way of populating theory space, when low energy parameters vary as a function of time during the cosmological evolution. You know, some people, just the word multiverse sounds like a metaphysical concept. But I want to make the point that it's actually a very familiar part of our everyday theory toolkit. Think of the axion. So the starting point is the observation that a standard model parameter, theta QCD, should be of order 1, according to EFT logic, but measurements of the neutron EDM tell us that it must be smaller than 10 to the minus 10. So to deal with the paradox, what do? We promote the standard model parameter, theta, to a dynamical field, the axion. And then during the cosmological history, the axion explores its full field range and takes all possible values in different patches of the universe. This is because the Goldstone symmetry makes all these configurations to be degenerate in energy. But then after the QCD phase transition, the axion potential creates a non-trivial vacuum structure and dynamically selects theta QCD equal to 0 as a preferred point. This is exactly an incarnation of a multiverse explanation of a low energy parameter. Okay, how much time do I have?
Sorry, John, may I make a comment?
5 minutes.
5 minutes. And now I'm gonna use the 5 minutes for the comment of Riccardo. Please use my 5 minutes.
Sorry, but still the point where it relaxes is dictated by symmetry, by the fact that QCD is parity symmetric.
Sure, sure.
So it's not truly a landscape.
Well, I mean,
you shoot and then you get, it's a clever landscape.
Exactly. I mean, certainly, it's a mixture between the two concepts. You see that symmetry comes in then to do the selection. But what I wanted, the point that I wanted to make is that the setup that you are using is something that really resembles a multiverse. In the same way that I was stressing, the explanation of Weinberg's of the cosmological constant. For me, an interesting point that I want to emphasize in the seminar is not so much of the use of which is a selection mechanism, but thinking in terms of a multiverse in order to address the question. So in the case of the axion, that's why I was giving this example, because I would say that you are using a setup of a multiverse, although then the selection mechanism, fully agree with you, is a symmetry. I think that, in the interest of time, I don't want to go over time. I had some comments about other mechanism with this approach. So, but let me skip them because I think it's more interesting than to have a discussion than me to talk. And so let me then make only one point. The organizers and Roberto told me that it's strictly forbidden. This is a rule of these seminars, strictly forbidden for me to talk about my own work. Okay, so I follow the rules, but I can't resist the temptation to mention my new paper, which appeared on the archive this morning, written together with Matthew McCullough and Tae-Wong Yu. It's a long paper, which is the result of a long lockdown. So the basic idea, which is, you see the link with what I was saying before, is that some parameters of a microscopic theory, and for microscopic theory could be the standard model or any of its quantum field theoretical extensions, are promoted to dynamical variables that depend on scalar fields that are light during inflation and therefore subjected to large stochastic fluctuations. Effectively, this looks like a multiverse, where standard model parameters change and fluctuate during inflation. The second assumption is that the microscopic theory undergoes some phase transitions as these parameters change. So just to give you an example, then to visualize this, think of the standard model and make the Higgs quartic vary. As you know, when the quartic goes below a critical value, then you start developing a new high field Higgs vacuum, and therefore the standard model undergoes a phase transition. Okay, so what we have shown is that if you take these two hypotheses and then you make certain assumptions on the potential for these scalar fields, then the scalar field is attracted towards the critical points of these phase transitions. This is an emergent property out of inflationary dynamics. Parameters are probabilistically driven, sorry for mistake, towards a condition of near criticality, such that the universe is at the verge of collapsing, at the verge of undergoing a phase transition. And we call this mechanism self-organized localization. This is a dynamical process. There's nothing anthropic in it. So we have used this mechanism to justify the near criticality of the Higgs quartic coupling, which I was alluding before, the smallness of the Higgs mass, and the cosmological constant. There's a lot of work still to be done, lots of open questions, but I think that our results indicate new directions which can be explored in particle physics to address some of our open questions in the field. Unfortunately, of course, rules don't allow me to spend much time on my paper, but I'm sure that I will have other occasions, other opportunities to talk about it. Instead, let me conclude by summarizing the main points of my talk. I said that we can imagine renouncing to naturalness by dropping some of its basic hypotheses. However, the consequences of doing so are even more radical than those of naturalness itself. These consequences lead to profound paradigm changes in particle physics. The LHC is having a gigantic impact on theoretical particle physics. We are confronted with a crossroads. Either the conventional symmetry paradigm is right, even beyond the electroweak scale, but its manifestations are more subtle than anticipated, or we are at the eve of a conceptual revolution, and we need to identify a new paradigm. Experimentally, we must pursue both directions simultaneously. We must explore deeper the high energy domain, and we must be open to all possible alternative options and alternative kind of explorations. Theoretically, everyone is free to follow physics instinct, personal taste. Personally, I'm very intrigued by the search for radically new paradigms, and I believe that self-organized criticality offers a new tool in quantum cosmology, which could unlock some of the mysteries of particle physics. Thanks.
Thank you very much, Gian, for the very clear presentation. So I see that there are a couple of technical questions in the chat, so maybe we can proceed with those questions and then go ahead with the discussion. Okay. So there were a couple of questions during your talk, Gian, but I didn't take trace of what exact point. By Giampiero, I see only the name. If you can raise your hand, I can, or just speak. I don't know if you can unmute yourself.
Yeah, I see there are also some private. I don't have the time to read them. So I want to alert the people who send me private comments that I can't read them at the moment, but they are welcome to make them publicly.
So Riccardo, maybe you can read, we can read the questions by Giampiero. I think it's Giampiero.
Yeah, but we would have to go back to the point where this. So now you can speak, Giampiero, please. I see you're unmuted, but we cannot hear you. Questions were about what about anomalies in standard model effective field theory, and what about mixing among scalars? But they need to be put into context. I cannot say exactly at which point they were asked.
I'm not sure that I understand the question.
Giampiero, we see you're unmuted, but we cannot hear you. So there's also a question to Riccardo. Can you see, Riccardo, the question in the chat?
Yeah, there is a question about.
Why don't you read it first, so we all know what the question is?
There's a question, if we take, by Ivo Sachs, if we take chiral perturbation theory as our EFT, not knowing about QCD, would we have eventually ended up with QCD, or could the EFT approach have led us completely astray? I don't know. I mean, if you do measurements, if you go in a situation where you have a very tiny pion mass, I mean, if you're doing physics way below the Planck scale and you're doing graviton scattering, will you, by looking at graviton scattering, figure out the whole theory of quantum gravity?
No, but I would say...
Ricardo, so, for instance, I could have a sigma model for pions. I could have a weakly coupled UV completion of the pion sigma model, even adding some West-Domino terms that mimic QCD. Depends at what level you're going.
I think, Riccardo, you reply to the question you talk in a sense that what naturalness is telling you.
It has nothing to do with naturalness, this one here.
Wait.
It has to do with, no, I don't understand. Maybe Ivo should say something because, okay, go ahead. I don't see naturalness mentioned here.
I'm just saying that what naturalness is telling you, as you showed, is that there is, it's giving you information about the cutoff, where new physics should arise. Of course, naturalness is not going to tell you the form of that new physics. So it's not going to tell you about QCD, but it's telling you about the energy scale at which you should find resonance.
The energy scale is in pi scattering. Is the scale where the scattering phases of order pi. That's the scale. That you know where the scale is, right? But this scale could be the scale. I mean, you know what? You could know if you look at the derivative expansion versus the coupling expansion, you can know whether the theory underlying is weak or strong. So if you see the underlying theory is weak, because there are two expansions that you can do, right? When you do an effective theory, there's an expansion in number of legs and the expansion number of derivatives. If you put these two expansions together, you can extract the scale and the coupling. If you see that the coupling is strong, then look for a strongly coupled UV completion. And now you ask Young and Mills and blah, blah, blah. Maybe you say, well, the simplest group where I can have, I don't know, SU3, you try. I mean, then maybe you match the West-Domino term. Perhaps you could have. If you found that the UV completion is weakly coupled, then maybe it's a linear sigma model.
So I see that we are already entering the discussion. So I think officially we should start the discussion session. And I would start, as promised at the beginning, I would start with the three members of this mini panel that we asked to start the first round of questions or comments. So if Martin Schmalz is ready, maybe I would start with you.
Baldassare, L'altro com'è?
So Martin, are you there? I don't see him.
He left.
So maybe, okay, so in the meantime, and then Martin is back, we can see if Raman Sundrum is
Now we need to allow them to unmute, I think.
right.
Yeah,
I just did it with Martin.
Okay.
Okay, you just allowed me.
Ah, sorry, Martin, please.
Yeah, well, thanks, guys. This was really fun and really interesting. So my thinking about, what, especially during Riccardo's talk, I really like this conflict that we've seen for a very long time between the simplicity and naturalness, and this was very nicely explained here. So the standard model, or that we're seeing simplicity in nature, tells us about a separation of scales, and then we're screwed because naturalness demands or shows us that there's a problem. But I see also in Gian's talk this idea of the multiverse. So it seems like simplicity and naturalness point towards the Higgs mass precisely as the one place where the multiverse can play a role, because those operators are the ones where scalar fields could play a role, right? If you add scalar fields to the dimension 4 operators, you necessarily end up, if there's a separation of scales, with very small corrections. But in the Higgs mass, you can make a big difference. And so I was wondering if there's a nice way of incorporating extra light scalars into your discussion, Riccardo, where,
So you're saying introduce a landscape in the Higgs mass. This is what you're saying. And then what? Then what? How it is selected? The question is the mechanism of selection, right?
Yeah. So the relaxion idea, very explicitly gave us a mechanism for how the selection might be happening. But I was wondering if there's a more general idea of, without the dynamics of that, right? The nice thing about effective field theory is that you don't have to think about the precise dynamics and the precise model. And so the question is, what are the general constraints?
Well, but but if you have this landscape, then the question is, what you need a story to explain why you end up where you end up, right? And this is not purely within effective theory, right? You have initial conditions that, am I missing something? So you would like to do relaxion without the relaxion mechanism?
Yeah, I would like to know, are there any constraints about just from the effective field theory perspective, without having to think about how precisely.
So for instance, if you take so let me understand what you're saying. So let's take the relaxion model and let's forget about gravity. And now there is this landscape and there are these local minima, and some of them seem to have the features. So then what? How do I proceed?
So, I think this idea fits very nicely within your framework. There are symmetries.
I'm trying to. No, I vaguely see what you're saying, but not vaguely enough. So I understand, but clearly not. It's interesting, but so this is why I'm asking you. So if I were to consider the relaxion, so what should I extract from the relaxion?
Well, I want to extend the principle of symmetries and spurions to this idea and ask, what are the very basic ingredients that you must have for this to have any chance?
Yeah, I don't know if I can comment. I understand it's a question addressed to Riccardo, but
no, go ahead, Gian.
I just
the question to me, maybe I cannot answer.
No. Martin, I think what you are saying is, to me, it seems orthogonal to the approach of the effective field theory. Because as Riccardo showed, right, the basic point is that you have a relation for the Higgs mass, and you're arguing based on, let's say, dimensional analysis, what that expression should be, and therefore that there should not be some coefficients are very small. The idea of, let's say, the multiverse, the relaxation, or self-organized localization that we approach, any of those approaches, is to exactly get rid of one of the hypotheses that any of that relation should exist. So there's no one formula for the Higgs mass. You can't do that. So it seems to me that you are, once you introduce an hypothesis like that, you are breaking down the argument of given by Riccardo. You cannot argue anymore about what is the structure of that equation that describes the Higgs mass.
Well, the question is what would be the vice?
Not a single value for the Higgs mass, but now the Higgs mass becomes this landscape of values, and the way it's selected is not by EFT arguments, but by some other arguments that could be cosmological evolution, critical phenomenon, blah, blah.
So the question was
there are lots of people.
Look. The question is how to include the vice in the EFT description. Should ask Martin Scorsese. I don't know. I mean, I don't know how to do that.
I think for me, it's really against that language. It's a departure. This picture is a departure of that. So trying to force it, that language, I don't think you're going to go very far. But I may be wrong. Maybe there is a.
But the idea sounds sufficiently crazy and vague that I think it's interesting. This is what I want to say to Martin.
Thank you. That's very nice of you.
No.
Okay, thanks, Martin. So I think there are many people who want to make comments or ask questions. So I think we can proceed to Raman at this point. Let's see whether I can unmute him. Raman, please.
So I wanted to again, I thank Gian and Riccardo for putting themselves out there on this tricky subject. I wanted to propose the middle way, partly because I see it as pragmatic. Riccardo brought up the point that there's a lot that we understand. The standard model explains a lot about what we don't see, right? Like proton decay, et cetera, flavor changing, neutral currents. I just want to note that taking that as very, very important evidence, what we don't see falls into two categories. Things that we don't see, but if new physics showed up, not at 1 TeV, don't fly so close to the sun, but if it shows up at 100 TeV, okay, which is the limits of, say, our human ambitions, 1 PeV, for what we can hope to do in the future, then a lot of these things that we don't see would automatically be explained by, again, the standard model effective field theory. A lot of things that we don't see would decouple, even though there's new physics, massive new physics sitting at 100 TeV. The one exception is proton decay. And in model building, I would say it is relatively simple for BSM physics to avoid proton decay, the absolute biggest catastrophe. But other things, new physics could show up if it is merely delayed from the expected TeV scale of 100% naturalness to whatever, tens of TeV, 100 TeV, let me just say 100 TeV to satisfy all comers. So that is within the scope of human ambitions to reach energy scales like that, to build future colliders, to start looking in experimental direction. So we have to ask, why would naturalness be frustrated in this way? Why is it not perfect naturalness? And to me, this idea of frustrated naturalness makes logical sense. If one takes the multiverse backdrop that Gian introduced, as the basic idea that parameter space is turned into space on the most vast superhorizon scales, that makes sense to me logically, that those are actually solutions to effective field theory equations of motion. So what Gian said makes perfect sense. But the idea that theories, the world that we inhabit is some sort of a compromise in the multiverse between naturalness, which is just keeping your eye on one thing, is the Higgs mass fine-tuned or not, and other things that are anthropically imperative. For example, baryogenesis. So I like to point to this model that Gian Giudice wrote several years ago, which is a supersymmetry R-parity violating model, in which if the model is finely tuned so that SUSY breaks at 100 TeV, you have successful baryogenesis. If you have the completely natural model with TeV supersymmetry, you have zero baryogenesis, so that there is a frustration of naturalness by another anthropic imperative, which may really tell us that new physics is somewhere within reach of humanity, but it's not showing up at the expected TeV scale. This general idea of frustrated naturalness I see in a number of models, including by some people here, in different guises, and I wanted to propose that as the middle way, which allows experiments to sort of see what they're trying to target.
Yeah, by the way, Raman, my next transparency was precisely in this tone. In fact, my next transparency is also quoting, see also talk by Raman Sundrum, HEFT 2016.
Yes, I think
the
that's
middle of the road option. Yeah.
Yes.
The middle of the road. Yeah, also dark matter, right? If you have, could you also argue for dark matter, strongly coupled dark matter, 50 TeV?
You could, and it has been argued by Luca Vecchi, who you know very well.
Luca Vecchi.
So this has happened a number of times. I see Michael Geller sitting here. He has versions of this principle of naturalness, which you can think of as playing out in a landscape or in a multiverse setting, but undercut by some other anthropic imperative. Is a very I think it's, again, perfectly reasonable, logical sense, but it puts the experiments in the driver's seat, because you might say, what if this very logic of frustrated naturalness frustrates it so much so that the new physics is sitting at 1,000 TeV?
No, but this is important, Raman, also because this idea of theories that are a bit more tuned but simpler, this enhances the importance of indirect searches.
Exactly.
All precision, EDMs, KK bar. I mean, like the future 15 years of LHCb, where they will improve the CKM fit by a factor of 10. Yeah. This is important because.
So I believe that's why I say I think it puts experiments in the driver's seat, which I think is the true job of theory. Is that I think this gives a logical, philosophical framework in which the experimental search strategy is at its broadest and richest, and the renaissance of theory experimental collaboration that Gian referred to, which when he pointed to it, he said maybe was a little, it's rich, but it's not motivated by a deep fundamental viewpoint. I think with this in place, it has that deep fundamental viewpoint while also having the close collaborative ties.
If I may show just one transparency that I like, just very quickly, 30 seconds as a reaction to Raman. Robert.
Yes.
Sure.
Okay. So this one here, right? So this is showing what if you want the perspective on experimental searches, okay? There is simplicity and naturalness on the two axes. So naturalness is pushing the scale of new physics down, okay? And simplicity is pushing up whatever coupling violates flavor. If you don't want to use all these bazooka of all sorts of crappy flavor symmetries. These couplings are bigger, okay? And so you see that there's an interplay. There are situations where the couplings are large, so they're simple and natural, and these are killed both by precision experiments and the energy frontier. But then there is precisely this complementarity between searches at the energy frontier that search natural theories that are complicated and precision things that search unnatural theories that are simple, okay? So I think these have equal dignity in our experimental program. So this is in this perspective. I didn't have much else to say.
If I can comment, I agree with you. I think it's wise. Now we sort of presented the two extreme in a sense, Riccardo and I, and you, Raman, at a wise.
I also had this one. That's Raman. You see Raman, just to defend myself. By the way, this transparency.
I'm not laughing because of your joke.
I absolve you, Riccardo, of all sin.
Yeah, Raman. I always have you in my mind. I mean, at night before going to bed, I think of Raman.
Okay, so I think thanks, Raman. And at this point, we can pass to Lian Tao. So Lian Tao, please.
Okay, yeah. Thanks for Riccardo and Gian for this excellent discussion. So I just wanted to, so I think the discussion just between Raman and the Riccardo just sort of made one of the comment I was about to make. And I think when I sort of enter physics, we're already in back then we're already in this little hierarchy era and the clever model era, right? So we are facing with multiple hints that maybe the from flavor, from CP violation, and so on. And but maybe because of that, I always don't really feel that the little hierarchy problem is as big of a problem, even though I think I also worked on it and so on. And I think certainly the point had already been made. I think I'm very sympathetic, to the idea that the physics may be at just slightly higher scale, and the theory will be simple, yeah, I think to that end, I think LHC actually hasn't changed that picture that much, at least to me. So I think I think before the LHC, I see a big
I agree with you. Yeah.
Trend that if you think a little hierarchy is a big problem already way before LHC, that should be a problem. Okay, so that's a very big problem already. And anyway, so that's just my comment and on this in this regard. And I have a sort of a question that I think of course a lot of the new ideas has been developed on naturalness, and of course we wanted to also think in terms of in the context of planning the next step for high energy physics. I haven't followed all of these the ideas. I follow some of them. And so as we know, lots of discussions in recent years. So basically, I think in the near term, we're going to do a lot of precision measurement. We're probably going to improve the precision of Higgs by a lot, and so on. And in the further down the road, we're going to going to higher energies, trying to probe deeper into the energy frontier. And a lot of these, some of these new alternative ideas of addressing naturalness, they still, either feature new physics around the weak scale, and all, Higgs is the only lamppost. You can try to probe this kind of new physics. So in this regard, it seems that that approach is correct. We are still going to, no matter what, we're going to make progress based on this this kind of plan. I'm just wondering, are we missing anything? Are we, in terms of planning the future, are we, are we missing any new probes, motivating, new experimental probes and so on in addressing the naturalness problem? I mean, it's a bit of an open-ended question, but that's I think that's my question.
Certainly, the high energy frontier, as we're saying, is very well motivated, and it's not just a matter of saying, okay, we've we have not seen new physics that far. So we just tune, we accept a little bit of more tuning just to justify the next experiment. I think Raman put it very nicely that this compromise may not just be a fact of tuning parameter, but it adds its own theoretical dignity. It could come out from either anthropic motivations or other kind of selection motivation, or really the need of nature to make compromises, because otherwise could not create the right universe for us to live in. So this is, I think it's a very important message also to pass it to experimentalists, that we're not just telling them continue the search because so far you haven't seen anything, but there is a dignity, a logic about going further. Since you mentioned, however, other direction, I really wanted to stress also with my talk and with my attempts to go in new directions that we should not leave out other alternatives. I was giving my reservations for this bottom-up approach, but Raman, I was also emphasized the importance of it. I'm not going to work on the little models, but I support very much the research, the experimental research that goes in that direction. Because as I said, I think it's extremely valuable. Because when the moment we don't know the direction, we need to explore that. It's simply my own taste. I'm not going to tomorrow. I'm not going to work on the model first. That's not saying that diversifying the spectrum of our research, I think, is extremely important from the point of view of naturalness, and in general from the point of view of how should we address big questions. Of course, a way to proceed in that case is to do it with a bottom-up approach, to construct little models and then be really following the experimental opportunities, seeing where I can go, where I can explore parameters range, which so far has been left.
But that possibility is kind of infinite, right? Isn't?
It's an infinite, of course, approach that has to be done wisely, has to be done a sort of judging what are the best direction. And it's in the same way nature has to make compromise. We have to make compromise about our resources to see what are the experiments which are valuable. You know, going in certain direction is something that we will learn knowledge. I think that we have, you know, when we judge new experiments, I think one measure is to say, what is the knowledge that we're gonna gain from that experiment, no matter what the result is. You know, even if the result gives, even if that experiment gives a negative result, are we gonna get some new knowledge out of that? If that is the case, I think it is a worthwhile direction. Certainly, the high energy frontier at the moment is the most promising direction, because it's really the one that opens up directly this black box that we still have in front of us.
Okay, thanks, Liantao. Now we continue our session with other questions. I think David E. Kaplan is first. So David, let me try to unmute you. Okay, please.
Hey, thank you, Roberto, and thanks, Riccardo and Gian for, it was fun to hear talks on naturalness, which normally make me sick, but I'm very excited to see both of you, and I miss all of you, so this is a great opportunity. And let me
saying, despite of the subject, I mean,
despite of the subject, I'm having a very good time. I'm having a fantastic time.
That's very good.
Let me start my comments by saying I regret everything I've just said, because I might forget to say that at the end of my comments. So I deeply regret all the things I've just said. So here's what I'm going to say. First, I want to address what Martin said, which I think maybe there's something interesting there. I understand that.
No, by the way, I was not making.
No,
I think I took it seriously. The only thing
I agree. Let me just say that the things you do when you try to solve hierarchy problems with relaxation or dynamics or history, you know, the problem of putting it in effective field theory is it's based on history. It's based on things like initial conditions or trying to create insensitivity to initial conditions. Initial conditions are the bane of the theory of everything. You don't want to be sensitive to initial conditions. So we put initial conditions often separately from everything else. But the core parts of those relaxation theories are that first you're sort of solving the stupid Weinberg paradox and solving the cosmological constant problem, which is that V, the potential, and V prime is very tiny in the same location. So that looks like a fine tuning. But if your potential looks like this, or if it's just flat, very tiny slope, then you've solved the V and V prime are small in the same location. And that's the solution. But then how do you end up in the vacuum that you want to? And that requires often some kind of trigger mechanism. And so when we tried to build these models, that was almost all of the work to figure out what was the trigger mechanism to stop you in this location and that. But in terms of effective theory, and also this a little bit addresses John's crapping all over little experiments that are not high energy physics, is that that dynamical approach as a framework is that there are very light particles. There are light scalars, period. And there are things that need to scan parameters, and the scanning of parameters over very long times require very light particles. And so there should be, in principle, a general program to search for very light particles. And if you believe in quantum field theory, as we all seem to think it's very compelling, then there are not that many couplings of very light bosons to the standard model. And you look for all of those. And that, to me, outlines a very clear, almost trivial experimental program that we have ignored. I don't believe we're going to make big discoveries by committee. So we're all gonna argue with each other here, and we're not gonna discover anything. But what we are doing is helping people, inspiring young people who may be still on this talk, to vote with their feet. They'll listen to all of us and they'll say, well, this sounds compelling, this is not. And that would be great for a diversity of opinions, because what we've done for the last 30 years is theorists say things like, this is a miracle, and then an experimentalist that probably only have 4 high quality big experiments in their lifetime go for the top theory and try to discover that. So the vast majority of dark matter research has been in looking for a WIMP, the vast majority. And now what's going to happen for the next 20 years? We're all going to be looking for the axion. My God, this is crazy. What if order 1 fraction of the experimentalists are looking for parameter space, are looking for dark matter masses over huge ranges, as opposed to some preferred specified thing? The fact that we can discover ideas that Surjit and Peter and the other people who are trying to come up with tabletop experiments can come up with ideas that hit huge ranges of parameter space are suggestive, since those ideas could have been done 20 years ago, are suggestive that there's an intense narrowness to our field, which I find completely ridiculous. And now I listen to Riccardo's talk and I hear about naturalness, and it's very clear. You look at them and you say, yes, it's important maybe to work on models, but the experimentalists are supposed to answer that question, and most theorists should no longer be working on that, because we've already seen that it's either simplicity or naturalness. And we have spent 30 years making the damn theories less and less simple and uglier and attempting to create something that's discoverable. As long as we've parameterized the unknown in such ways that experimentalists can go after it in new ways, new phenomena, that's great. I think we're doing a good job.
I was only the ambassador of this.
I know, I totally, like I said, I'm going to regret everything that I've just done. So that, I think that's all I wanted to say. I think generally, I think maybe thinking about light fields and effective field theory, and just maybe there is something there vague with respect to what Martin was bringing up. I think it's interesting. I think the fact that these new solutions depend on the history of the universe, which means initial conditions or avoiding initial conditions or triggers and things like that. To me, that's a new approach. I think the anthropic approach is part of that because it's a trigger in a sense. But what we want to do is generate ideas for places to hit the frontier. And yes, the high energy frontier is always there. Whether or not we believe it's important, it's always there. It's a real line of knowledge. But the other line, which is equally valid, is weak coupling. And I don't see now, Before the Higgs, the LHC was the game changer. After the Higgs, the LHC is a fishing expedition. And so I put it at the same level as looking for things that interact with us at weak coupling. I don't see why energy is the only barrier for a threshold. There are so many things that could be weakly coupled to us, we don't know what they are. And that could solve the hierarchy problem. It could solve the CC problem. It could be what dark matter is. There's no reason that all these problems are solved in the UV. So for me, I find it crazy that we're dominated by UV, but of course, like I said, I think we're going to be dominated by axion searches for the next 20 years. So be careful.
Are you saying that we should stop completely the high energy program?
No.
Okay.
Look, I'm saying order one factors. If order one of the people looking for dark matter in the last 30 years spent time on the axion, other light fields, other particles, perhaps we would have some more interesting things to say. I don't know. I'm not saying give up. I'm just saying that as theorists, we have to think a little bit about how we bias what we think is interesting or not. And I think we've lost our way a little bit. And that reflects itself in the experimentalist who is very good, wants to look for the top dark matter candidate. Why would they go for number 2 that's only mentioned in every 10th talk? And so every person looking for dark matter is going to do a WIMP. And we're going to go deep into the WIMP territory. It's not Z mediated. It's not Higgs mediated. Maybe it's a tune thing. Maybe we're down the throat. Maybe it's okay. My God, dark matter masses have a range of like 80 orders of magnitude. And we've been hitting the weak scale so intensely hard. Dark matter is something we know is beyond the standard model. The LHC is a fishing expedition, not a bad one. We're all afraid to say things like that because we think it'll collapse the community or the experimental effort. Of course it won't. Those things are very important. But we've done it at the expense of just
you were talking about dark matter.
target experiments.
Sorry, David, stop a little bit. So I thought you were talking about dark matter. And now you're talking about the LHC as a fishing expedition. So, I mean, you were talking about dark matter or about the LHC? Sorry, I don't understand.
I regret.
Just mentioned, it just came out. You said, oh, fishing expedition. But you were talking about dark matter, right?
No, what I'm saying is that...
Are you suffering from some Tourette syndrome? Sorry, you say LHC is a fishing expedition.
No, I'm saying the LHC is a fishing expedition in the same way that every experiment we do is a fishing expedition. In the past, the LHC was a guarantee. It was a place where we were going to cross a threshold for which we had to see something, or something non-trivial was occurring in this case. And now we're not at that case. Now we're talking about naturalness as a guide post to try to understand what's going on. But it is like any search for new physics. It's a fishing expedition. We do learn something.
I would say that the LHC is a machine to study unnaturalness.
Yes, isn't it? Aren't we already in an unnatural situation? So it's studying how much more.
I mean, of course, you may say it's very expensive, but knowing that something is fine-tuned at the level of 10 to the minus 4, I think it's interesting.
I do too. I think it's interesting too, but it's not the only interesting thing.
No, there are lots of interesting things to do, David.
Yes, there are lots of interesting things to do. That's right.
I make a comment. So first of all, you misunderstood me if you say that I was crafting over the little experiment. On the contrary, I gave a full slide to give you the reasons why. Then after that, I said, well, just among us, we just say, I was talking with the people on the camera. I had no idea that you were overhearing us. Jokes aside, this was just more of a personal taste of what I like to do, but there's nothing to do with the physics program. I think it is clear, but I think this is by now, it's something that is accepted by the community, that certainly we need a variety of directions more than ever. And so these explorations of the, let's say, high intensity frontier, whatever you want to call it, is crucial. It's very important, and it could be the right direction. Definitely when you're looking for new direction, you cannot just follow one. However, I disagree when you say the LHC or say, future high energy collider is just a fishing expedition because the Higgs, because naturalness we've tried so long. Remember that the high energy frontier is not just testing the Higgs and testing the naturalness, okay? It's an extremely broad program. And we have to remember that it's becoming, if you look at the results from the LHC, it's a broad program in precision physics, has given us a lot of information in that direction. You know, we were talking about the LHC B anomalies. You know, you can say, oh, this is a strange direction. Well, it's coming from the LHC. So I think that it's narrowing down too much the high energy frontier by just associating with one particular question. The high energy frontier is a broad spectrum of research that has an incredible value. And so comparing the full spectrum of high energy frontier with one single experiment looks for the axion, I think it's unfair. I mean, I think that it's true that both should be followed, but you can't just put a one-to-one direction.
Of course, the axion experiment is small. I'm saying that all of those experiments, all of the effort going for light.
Look, David, after your comments, I hope that the flavor anomalies will stay and get better. And I would like to see you to work on the flavor anomalies. Then we go.
As Raman knows, I'm a walking Born approximation. I can't calculate loops. Yeah.
No, we do it 3 level. It's all 3
okay,
level.
I can do 2 then.
Which is
left of quarks.
Non-perturbative, and we do it as a 3 level.
I would be very happy. I would be very happy. Of course. I would not be able to compete with the other 375 papers that come out that day when it gets to 5 sigma. I would not. I can't. I'm not that.
The crucial thing is to avoid to use flavor symmetries.
But I'm very interested.
Will have to be a paper without any flavor symmetry. Then you have your own domain of action, because out of the infinitely many subgroups of SU3 to the 5th, we use the empty group. Okay, and then we do and things.
Then you're going in my direction. That, you know, I'm very excited about the flavor anomalies. I'm less excited about the theory attempts, exactly because
that's exciting. You can become a pope. Okay, go ahead. Yeah.
They're just kind of a repetition of what I was calling the symmetry paradigm. Again, don't misunderstand me. I'm not crapping over the symmetry paradigm. I think it's a fantastic achievement and could be right. It's just that at the moment, I think that we have seen that there are so many other directions we could explore, and as a theorist, it's natural that we are more attracted to that. So I hope that I certainly hope that the flavor anomaly will stay, but I also hope that they will lead us to something new than just repeating the structure of symmetries, getting bigger gauge group, or repeating Patti Salam to the 5th, and so on. But rather that will lead us to new concepts that can change the paradigm of particle physics.
Okay, thanks, David, for your comments. So time flies and we're getting late. But there are 2 raised hands. So I will go through these 2 raised hands, and then I think I would stop the session. Also because there is a Q&A session on the webpage, so everybody can, in principle, ask questions to the speakers, and the speakers are encouraged to to answer all the questions. So Marcus is next. Please, Marcus.
Hi there. Yeah, this has been really interesting for me. It's been a little bit like a therapy session, and it's great to see so many people here I know and I miss. I'm looking forward to seeing you. So I'm just going to give some comments. I don't know if there's a chance to respond. This has really made me, these wonderful talks have made me sort of look back, step back and see what, think about the big picture, which is very nice. So I just want to tell you what my thoughts on this are. So, first of all, I think that Riccardo very nicely reviewed the great, paradigm that we have of quantum field theory and effective field theory. To me, that seems like one of the great products of thinking of fundamental physics over the last many decades, and something that is, you know, as John very nicely said, you have to be both crazy and very ambitious to try and doubt those things. So on the other hand, I think when we talk about naturalness, I think we should keep in mind that predictions based on fundamental principles, solving fundamental problems, has a much less successful history in our field. There are some notable examples. They're great and valuable, and they're among the greatest achievements of our field, but that's not how most things are discovered. Most experimental discoveries are serendipitous, okay? And I think that's something that we should keep in mind. And in particular, naturalness, which is the subject of this thing, has an even less successful history. It has, again, some very prominent examples which we should treasure. And to me, it's very significant and important that ideas like anthropics or self-organized criticality or these things all in my mind have in common that they impose some kind of IR boundary condition on our theory, whether it's the existence of life or you know, or some cosmological history. And it, you know, they give us examples where things that, you know, we would like to think of as fundamental parameters just aren't. They're determined by other kinds of physics, which we may be able to explore and so on. And so I think for me, this is a little bit of an existential crisis for our field, because we have been thinking in terms of going to shorter distances, discovering new physics, discovering new principles. And, you know, we have to face the fact that perhaps this is not the way things work, although it might be also. We shouldn't give up. So the last thing I just want to say is that I would just strongly suggest that we not think of the high energy physics as a fishing expedition. I think a much better analogy is that it's like the search for life on other planets. If we go look for life on other planets, we want to do this because it's incredibly interesting. It's incredibly important. Do we have any guarantees that the next round of experiments are going to find life on other planets? No. But what we know is that we can go into new territory. We can address an amazing question that's incredibly important to us. And I just think we do have to start thinking about it like that, and not also, you know, not necessarily think about just short distance, you know, mourn too much the loss that it may not be that short distance is not the place to find out what the parameters of the universe are. So that's my comment.
John, please.
And I generally agree with everything you said, and I repeat what I was saying before because it goes along with what you were saying. I mean, when we are looking for new experiments, it's exactly what we have to value is the knowledge that we gain by doing an experiment, and that has some merit. And we can understand what is the knowledge even before doing the experiments, even without knowing what we'll find. And I think that is an important aspect. You said that most experimental discoveries are serendipitous. It could be well true. We could do a statistics and find out. I think you are correct. But I would also add that most of the breakthroughs in the history of physics are not coming from serendipitous experiments, but from pure thought, from the theory. Those are really the ones that made the big steps in changing our view. So I defend that point very much.
Riccardo, you want to add anything?
No, I don't have much to say.
Okay, thanks, Marcus, a lot. And then we go to the last question by Michael Geller. Michael, You should
Hi.
be unmuted. Okay.
Yeah, so thanks for the exciting talks. So I have a more practical question maybe for Gian about going into this direction of solving the naturalness problem with cosmology, and specifically with light fields that have stochastic behavior, let's say during inflation. And that is what I also encountered when I was trying to do some of this, which is that the major problem is, of course, the measure problem in eternal inflation. So is there anything new to say about this, on how to avoid it, how to bypass it, or is it truly going to hinder us forever in this approach, specifically if we want to find any true prediction for the theory? So that's my question.
Yes, of course, it's a very good question, and I don't have anything new to add, except from the fact that this renewed interest in this question, I think we will revamp the research in that direction. The research in that direction sort of died out after the beginning, and then people achieved some important results, but then nothing more happened. I think now it's a moment, because of these new motivations that people like you and also this work that I've done, it will, I hope, make people think more about these questions. I don't think there are unsolvable questions. It's just that there are big puzzles, but they're not necessarily unsolvable. Now it's going to be really a challenge for the theorists to make more sense about eternal inflation and trying to make sense about its probabilistic interpretation and defining in a proper way the measure problem and the meaning of any interpretation. The fact that it's a difficult problem should not discourage us. That's why I was giving the example of inflation at the beginning. During my talk, I was saying, well, in the beginning of inflation, say, okay, it's an abstract idea, I cannot go forward. Well, then people were smarter. I think now we are in the similar situation. I think more people, I hope, will be encouraged to look back at these problems, and I hope that progress can be made. But I cannot offer you today any progress on that specific question. But I'm not pessimistic. Okay, I think that these are addressable questions.
Okay, thanks, Michael. Thanks, Gian, for your answer. I see that there is another raised hand by Alexei Boyarsky. Alexei, if it is something quick, we can go over. So let me unmute you because we are very late, please.
Yeah, it is a very quick question to Gian. Among your postulates that you said you do not want to reject behind naturalness. The first one was about the absence of a new scale. And I mean, apart from accepting that we do not understand the nature of gravity and it's not guaranteed, as for example, Hooft said in his Nobel lecture, it's not guaranteed that effective field theory approach and our differential geometry-based physics, continuous physics, can be applied to the quantum gravity. Apart from this, what would we lose fundamentally if there is no new scale? I mean, it's a rhetoric question. You know that all phenomena that you describe, neutrino masses, everything, they all could be explained without any new scale. Only gravity and Landau pole by Riccardo is above Planck scale. So if we get rid of Planck scales, and together with it, Landau pole goes away.
What do you mean you get rid of the Planck scale? And what about the scattering of gravitons? So this is not the scattering phase of gravitons does not contain the Newton constant. If you can do the scattering phase in the S wave on gravitons, you're saying that this doesn't make sense, that gravitons do not exist as quanta. This is what you want to say. Is this that you want to say? There are no quanta of the gravitational field. There are only classical waves.
Sorry, I was muted again. Yes, I want to say that the nature of quantum gravity is something
classical,
very different.
Exactly classical. That is not, there's no way you can make sense quantum mechanical of gravity the way we understand it. Because the moment we do entertain this, then we can do graviton scattering, and the scattering phase in the S wave or whatever, it's S over m Planck square.
So are you talking about,
exactly, it's exactly like pi scattering in QCD.
Are you talking about gravitons or gravitational waves? You said classical and then gravitons.
The quantum of the gravitational field. Or similarly, I can talk about the gravitational scattering of ordinary particles.
My question to Gian was that I accept that we would need to accept that we do not know what quantum gravity is. And here I agree with you, Riccardo, I don't have an answer, right? So I forget about gravity. I do not treat gravity quantum mechanically. I accept that I don't know what it is.
Too vague. There's no gravity, there is the Landau pole of QED.
The question was, apart from this, do we lose anything else or not?
Okay. Can I answer? I totally agree with Riccardo that, just saying, well, we can ignore gravity is a little bit vague in itself. But there's even more than that. As I said, it's not an excluded possibility. It's still possible that there's only one scale, and then there's no issue. Practically, I really don't see that how this can be implemented.
Sorry, I would like to understand the statement, there's only one, there's no scale, to really see it concretely. Because, for instance, and naturalness does it in a sense way concretely. There is another scale, but it is in another sector, and there's a precise selection rules that avoids the mixing. That's a very concrete statement, what Alessandro did with A natural, I mean, whatever, A string, whatever, A something, A gravity, okay, sorry, I forgot. So that is a concrete realization of this idea. And this, you can see and study it, and that's very concrete. So let's talk about that. That's very concrete.
No, I was talking that, I was saying that as a phenomena can be explained without news.
Yeah, but this is too vague. I don't understand what you mean by that.
What is too vague? Neutrino mass, you don't need a new scale.
Inflation,
you do not need a new scale.
There is no scale. I mean, so then we don't know quantum field theory. So you're saying, I don't understand.
I'm saying that there are many.
Well, I don't understand it. So that might just perhaps just me. Okay.
Many extensions of the standard model can explain neutrino masses without introducing new scale about electroweak scale.
Giving up the reason. I mean, this is one point that I was making. Essentially, giving up even the possibility of explaining things. For instance, neutrino masses, as Riccardo was saying, they have a logic with the standard model, so we understand this model. Now, instead, you're saying, well, I can give up the logic and then put it right-handed neutrino mass by hand, and then the problem solved. You are giving up any explanation, flavor. You're giving up the explanation by pushing the scale down. So it is a possible approach, but one should really then show that you can do it. And realistically, it means giving up any explanations. That's why I find a limitation.
I agree. But
Alexei, perhaps going towards what you're saying. Okay, let me just say perhaps in a different way. So you're saying that all this stuff about selection rules does not apply to gravity, period. Okay, and there is something really magic about the way gravity works, which defies selection rules. It's possible. Okay, maybe there is a symmetry that goes beyond the transformation of parameters, the effective theory, something that mixes fundamental UV and IR parameters in such a way that we cannot describe. It's not a symmetry that you can see when you truncate the theory. It's like what Nima was saying a month ago. It's possible that because of that, and if there is no new scale up to gravity, something magical happens. I'm not denying that this is possible, but to really make this very concrete, I don't know how to make it concrete, Alexei.
No, I absolutely agree with you, Riccardo. I also don't know how to make it concrete. I am a modest man.
I agree with you. I would be very happy to think, this is why I think this is one direction to go, that you think of a theory that is for instance, is a nullscape. There's no landscape. There's only one UV completion of the standard model. There's no option. And in that UV completion, the X mass is whatever, 10 to the minus 32 in fundamental units.
if you insist on
that's the way it is, and that's the way it is.
If you insist on a concrete explanation of what's going on with quantum gravity, I have no answer. If Gian insists that we need to explain all constants, I would buy also this. I'm a modest man. I'm not trying to do that.
No, I don't want to explain. I want we have to understand the qualitative features of the work.
But I would insist that together with 10 to the minus something coupling for sterile neutrinos, we would explain at the same time 10 to the minus 5 coupling for the electron, right? If we explain all this all together, I will be the happiest man in the world. But as long as we do not explain 10 to the minus 5 for the electron, I do not see any problem.
The 10 to the minus 5 of the electron is a piece of cake, Alexei. Because actually the hierarchy in the charge sector is more measured by the mixing between interfamilies. You have three families separated by a factor of 10, 100. This makes, within three families, 10 to the minus 5. So actually the hierarchy in the charge sector is not 10 to the minus 5, it's much less. The structural parameters are like the Cabibbo angle and BCB, and these are much bigger. And so everybody working on flavor appreciates.
So you say that if electron would be 10 times heavier or 100 times heavier, you have a no-go theorem for that.
No,
right?
no, I'm just saying that the structure, if you look at the charge sector, the separation of levels is not 10 to the minus 5, but it's 10 to the minus 1, 10 to the minus 2. So that's the real parameter. That's the seed of the hierarchy.
Anyway, I see on the face of Roberto that I must.
You promised that he was quick.
No, but it's not the fault of Alexei.
I know. No, but I think now it's we are late, and I think it's really time to stop. So I would first of all, I think it was a great discussion. So I'm very happy. I would like to thank the two speakers very much for their enlightening presentations. So the next event of the GGI will be another focus meeting. This will be on June the 9th, and it will be on the precision legacy of the high luminosity LHC. So thanks to everybody, and see you on June the 9th. Goodbye.
Bye, and thank you.
Bye. Bye.
Bye.